Hey, what's up, YouTube? I think that we're live. How's it going? We are joined by Luna right now, and it is a pleasure to be practicing mathematics again with you all today. So today is another hobbyist discussion group session. We will be working some problems. Yo, we already got one or two people in the chat already. Thank you. Thank you for tuning in, everybody. Okay, cool. So how's everybody's week going this week? For those who have been following the series, I wonder what people think of the most recent videos. I have a bunch of questions for the hobbyists, but let's just jump into some problems. What problems do we want to begin with? Kind of want to just like rip through a bunch today if we can. I'm thinking of starting to do review videos. So just hitting all of the topics that we've covered so far and working a problem from every section. So if we did that, why don't we just jump right into a problem from section 2. The next problem that I have not worked in this section is Lang 1.2.5. I haven't looked at this one yet. If anybody has any... Oh, my iPad's not showing yet. My bad. Whoops. All right, you should see my iPad now. How's it going, everybody? All right. If anybody has any specific questions that you want to ask or topics to cover, really just anything. Like this is your time, is how I see it. So I know I'll just be ripping through problems if we don't have specific questions, but I'm happy to work anything or take any questions. So 1.2.5, this is about rules for addition. Rules for addition. Hey, Luna, you're so cute. You're so annoying. All right, so A minus B quantity. What? My pen stopped working. Is it out of batteries? No, it just disconnected. All right, so A minus B quantity plus C minus D equals, we want to show that this equals A minus D plus C minus B. Okay, so to prove this, a lot of people in my videos have commented, yo, what's up, Dark Cola? Are we not members only right now? We're supposed to be members only. Sorry, everybody, for kicking you out. What happened? I know I set this up correctly earlier. What's up, Dark Cola? What's up, Tony Ferguson? How's it going, y'all? Yeah, apologies. I hate to kick you all out. I don't know why it stopped working. All right, bye-bye. But hey, dude, Dark Cola, if you haven't seen the videos, I would love to get your thoughts on the Math Can Be a Hobby series, dude. If you haven't seen episode 1 yet, here's your chance. Check it out, man. I think you'd really like it. mathcanbeahobby.com. Yeah, I hate to kick people out, but yeah. All right, thanks. Thanks for watching. Okay, fixed. Sorry, everyone. All right, proof. For this, we rewrite to additions and use commutativity. So we start from the left-hand side and rewrite all the subtractions as additions of a negative. So a minus b is the same as a plus negative b. c minus d is the same as c plus negative d. Now that we have rewritten all the operations as additions instead of subtractions, we can use associativity, which says that we can drop all parentheses. Remember that the parentheses around negative b and negative d, I like to think of them as quotation marks. Really, this is like, remember that this is a number negative b and negative d. But these parentheses are different than the ones that are defining the order of additions. These parentheses are separating negative b as the negative of b. Now that we have additions, we can regroup. In this way, using commutativity. So this one is by associativity, this one is by commutativity. This step is by definition of subtraction. And now, well, we can apply associativity again. Associativity says that we can remove or add parentheses in any way we want with repeated additions. When it's just one operation, you can regroup parentheses. And now this is a minus d plus c minus b, again by definition of subtraction. And voila, we are done. Cool. Hope y'all enjoyed that. Any questions? Anybody have any topics or questions that y'all want to work today? It's super annoying that YouTube keeps messing up this thing about members only. This is not the only time that this has happened. And I know that I set it up correctly. Hopefully now it's fixed. I hate to kick people out, but... Alright, number 6. Oh wait, no, not number 6. Let's go to the next section. And let's work a problem from section 3. In section 3, we have this problem. For me, the next one I have not worked is this. Lang 133 says, obtain expressions for a plus b to the fourth and a minus b to the fourth, similar to the Cool. All right, so obtain these expressions similar to the cube of a sum and the cube of a difference. I think we get to call this one a proof. I'm going to call this one a proof. From the previous exercise, a plus b cubed, the cube of a sum is a cubed plus 3a squared b plus 3ab squared plus b cubed. Thus, a plus b to the fourth, remember that this is by definition a plus b multiplied by itself 4 times. That's the definition of a power. In my own work, I wouldn't show this step, but for the sake of explaining it right now in a video, I think it's valuable to show that temporarily. I'm going to rewrite, though, this is much more like what you would see in a standard proof. So a plus b times a plus b to the third power. Now we have a plus b times the sum Now we can use distributivity now, so we did distributivity, distributing a times the entire product and b times that entire product, because ultimately that's a number. A cubed plus 3ab a squared b plus 3ab squared plus b cubed. Ultimately that's a number. We could call it c or something. And we know that a plus b times c is ac plus bc. So here we have a times c plus b times c again. Now I can apply distributivity to get a to the fourth, 3a cubed b, 3a squared b squared, ab cubed. I distributed a in the first term. Now we distribute b in the second term. Let's go ahead and use commutativity at the same time. So a cubed b, 3a squared b squared, 3ab cubed, and b to the fourth. Now we can combine like terms and find every term with a cubed b, which are these, and group those together. A to the fourth plus 3a cubed b plus a cubed b plus, let's do a squared b squared, 3a squared b squared here, 3a squared b squared, a squared b squared, so we got those. Now ab cubed I got that one and that one. And lastly, the last term that I haven't written is b to the fourth. now we've used every term from the previous sum and combined them all into this equation. Now we can factor out a cubed b. A squared b squared and finally we can add those numbers. Cool. And I'm pretty confident that that is correct. Fun fact for those who are curious. These coefficients, 1, 4, 1, 4, 6, 4, 1, pop up right here in Pascal's triangle. For the cube, for this, for the cube of a sum, 1331, 1331 pops up right there in the fourth row of the triangle. A squared plus 2ab plus b squared pops up right there. In general, a plus b to the nth power takes coefficients from this, from Pascal's triangle. And it's slightly tricky to write out the entire thing, but it's a summation with binomial coefficients. Yeah, it takes just a little bit of care to make sure that you get it all correct, but from I equal 0 to n, what is it exactly? It's going to be this row is 4 choose k. This row is 3 choose k. And it's the n-dimensional version of the same problem that we've been working in problem 2 and problem 3. It's just for the nth dimensional, the nth power of a sum and the nth power of a difference. We can get with the binomial theorem, and guess what? You can even prove it with induction, which we've introduced in the most recent videos. So that's pretty freaking cool. Now, a minus b to the fourth, you can work through this yourself. I want to leave this as an exercise. well, let's just do it. I'll do it. A cubed minus 3a squared b plus 3ab squared minus b cubed minus b times the same thing. A cubed minus 3a squared b plus 3ab squared minus b cubed. Okay, now distribute terms and then collect like terms. So the only a to the fourth term is going to be from a times a cubed. There's going to be some a to the fourth terms, some a cubed b terms, some a squared b squared terms, some ab cubed terms, and some b to the fourth terms. So if we just find the right coefficients, then we're done. You could scan and look at all of the terms and see that every term matches one of these cases. So a cubed b. We can get a cubed b by multiplying a times 3a squared b. A cubed b can also be from this one. So adding those two together, thinking ahead and adding those two together, there will be negative 4 a cubed b terms. Then a squared b squared terms, we can distribute a times that one and then a squared b squared here. So we've got something feels off. Oh, yeah, this second one wasn't correct. B times a squared b squared. There, this one. Yeah. B times a squared b. So we have positive 3, positive 3. This is going to be positive 6 a squared b squared. And then ab cubed would be a times that b cubed, and we also get an ab cubed by multiplying negative b times 3ab squared. So following those two, we get negative 1 minus 3 is negative 4 ab cubed. And then finally, the only way to get b to the fourth term is right here. Negative b times negative b cubed, which is going to be positive b to the fourth. Cool. And now we're done. That's number 3. That's section 3. Next time we will work with even and odd numbers. Awesome. Any questions? Anybody out there? I see we got 3 people watching. Let's go. Welcome, hobbyists. Thanks for being here. All right, so I've worked a problem from section 2, a problem from section 3. I have, hey, Fred Astaire, thank you. Yeah, thanks for being here. I will jump forward and try to work a problem from induction. So I know that we've taken like a huge leap forward, and it might be... I don't know. What do you all think? Did you all enjoy these videos on induction? I wanted to introduce some new math topic, something that's truly new to most people. So it's not, this series is not just going to be relearning math that you've learned before. Like, I do want to introduce new math that a lot of people have never seen before. And I promise you that induction can be taught at this level. We don't need any of the other material in between in the book to learn induction. A lot of books, intro to proof books, will have induction in the very first section. So yeah, I think that it's a valuable thing to introduce it at this level. But if it feels difficult, or if you feel like you're not ready for this one yet, or it's too technical, or you're less interested in it, that's the best thing about being a hobbyist. That's okay. You can skip these. If you're not interested in learning induction, I'm not going to require it for the rest of the series. It will be valuable. Oh, you'd appreciate an intro to induction. Okay, heck yeah. Have you seen my videos? Just so I have context. Have you seen the recent videos about them? I'm very happy to represent that material, and I think a lot of people who are joining these haven't yet watched all the most recent ones. Oh, you haven't watched them yet. Okay, well, I'll give a rapid fire description right now. And then if you want to watch like a little more in-depth presentations, then you could watch the videos. But I'll give the rapid fire intro right now if you'd like. First, I want to say that every mathematical sentence can be written as some sort of proposition. Like a mathematical proposition is a sentence that is either true or false, right? Like 2 is an odd number is a mathematical sentence. It's a sentence. It makes sense, but it's false. It's incorrect, right? The idea of mathematical induction is that there are some claims that are claims on a number. So this is a proposition or an identity, an equation for a number n. The principle of mathematical induction is that if we can show that a property, or that a proposition, a claim, an idea, an identity, a formula is true for one, and anytime that it's true for one number, then it must also be true for the next number. Then so this might seem a little abstract or something. The analogy that everybody gives in an Intro to Proofs course is dominoes. If you can show that you can knock over the first domino, in other words, your claim is true for n equal 1, and that any time that you knock over one domino, it automatically knocks over the next domino. Then every domino, the proposition must be true for every number. 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, etc. Okay, so the classic that you'll see in the video from before is this can be proved by induction. So the base case, when n is 1, the question is the identity, is this formula true when n is 1? Yes, because 1 is equal to 1 times 2 divided by 2. Like, what happens if we substitute in n equal 1? When n is just 1, the left-hand side is just the number 1. There's no other numbers that we add to it. And then the right-hand side is 1 times 2 divided by 2. And yes, 1 times 2 divided by 2 is the same as 1. So, therefore, the base case is true. Secondly, we have the inductive step. In this, we assume that the claim is true for some number n. It's at least true for the first one. It's at least true for 1, so we can assume that it's true for some number. Then we show that the claim is also true for the next number as well. To do this, we take the left-hand side, substituting m plus 1, and the sum of integers then would be this. Now, I can group by associativity the first n numbers, and by assumption, we assume that the sum of the first n numbers is this. By inductive assumption, or inductive hypothesis. We assume that it's true up to a number, and now we want to show that if it's true for one number, then it must be true for the next number as well. What we do is we distribute, and then convert the second number by doubling the numerator and denominator. I know that this requires a little bit of manipulation of fractions and being able to convert to a least common denominator, so I'm not going perfectly in order of the, like, every single thing in order, and like thoroughly studying fractions before using something like this. But we've seen this before, so I think that it's okay to do this one. Okay, cool. You have seen this before, but many years ago, and you remember this now. Awesome, dude. Awesome. Yeah. So now we get here, and we can do this a couple ways. First, you may know that you can factor this, like, you may recognize that you can factor that numerator, that you can factor this Yeah, it's a lot like series and sequences. The thing is that series and sequences, people will learn that as if that is a calculus topic, but series and sequences are honestly just a math thing. Like, sequences pop up all the time in math. Like, we study sequences like this in number theory and other forms of math. Calculus is like when you let the series be infinite. If you take an infinite series, does it approach a limit? But you can study finite series, or even this series, or this sequence of partial sums, of partial series. Like, this is an infinite series and an infinite series, like sum. So, like, this idea isn't only used in calculus, but we often only see it in calculus. Or like the first time that we really carefully think about sequences is in calculus. And that's a shame because it's just a math thing that's useful everywhere. Okay, so you may know that you can factor. You may see that you can factor that numerator. If you don't, what you can do is you can take the right-hand side, and we know that this you can take the right-hand side and substitute in n plus 1 into the right-hand side. So when we substitute n plus 1 for n, we'd have this. Really, technically, I'm going to write it just to be very explicit, like this. And, well, that's n plus 1 times n plus 2 divided by 2. And now we don't require you to know how to factor the polynomial. We can just do this by distributivity the way that we have so far. So using distributivity, we get this. And then we get n squared plus, skipping ahead a step, we get n squared plus 3n plus 2 divided by 2. So, therefore, the left-hand side ended up being this, and the right-hand side ended up being the same. Thus, the left-hand side equals the right-hand side. So, the proposition being true for n implies that the proposition is also true for n plus 1. Therefore, the proposition is true for 1, it's true for 2, it's true for every number, and we are done. And we get to draw the cute little square. So that's a classic introduction to induction. And it's a different proof. It's a different argument. It's also very beautiful. Like, some people might prefer Gauss's argument that I showed in episode 1. It's beautifully constructive. Gauss's argument, you add the numbers forward and backward. So if you add both of those together, then we get n plus 1 n times. So this is a constructive proof. And then this other one is an inductive proof. I think that they're both very beautiful. And one reason that I think that this one, even though it's like a little more fiddly and it requires a little more writing, a little more belief that this process works with induction, what's beautiful about it is that it applies in many, many other scenarios in math. So we can use the same idea in this problem. I'm pretty sure I've worked this one, but I thought I've worked this one by now. Prove that 1 squared plus 2 squared plus ... n squared. I have definitely worked this one. That this is 1/6 times n plus 1 times... Oh no, I just wrote it down, I think, in the most recent video, but I don't think I worked the proof. So let's work the proof. Yeah, I wrote it down as an example. The base case is true as 1 squared should be the same as 1/6 times 1 times 2 times 2 plus 1. So Luna. To write it out, I'd leave it like this. The base case is true as 1 squared is the same as 1/6 times 1 times 2 times 3. And you can fill in the details to prove that 6 divided by 6 is the same as 1 and 1 squared is 1. But in a mathematical proof, this is enough to convince the reader that you have thought about this. I think that that's a nice way to write this. The base case is true. Then assume, for the sake of induction, So we want to verify that the claim is true for n plus 1, for the next number. So the left-hand side, when n is n plus 1, would be 1 squared plus 2 squared plus ... n squared plus n plus 1 squared. And just like in the last problem, we can group to the first n as this by assumption. Oh, wait. Oops. n plus 1, 2n plus 1 divided by 6 by assumption. So by the inductive hypothesis, or the inductive assumption. Those are just two different ways to say the same thing here. Then this we can distribute. Maybe I distribute n into the second term and keep n plus 1 factored. 6 times n plus 1 squared over 6 Now, we'd have all of this combined with a common denominator. On the second term, n plus 1 quantity squared is n plus 1 times n plus 1. I'm going to go ahead and distribute now the 6 into the first n plus 1. So 6n plus 6 times n plus 1. Then I can factor n plus 1 maybe I kind of... I don't know if this is any more clear writing or not, but now n plus 1 is factored out on the left. I'm using distributive property to factor out the common factor, and we have that common factor of n plus 1, and then 2n squared plus n and 6n plus 6 collected together in the next term. Now, what can we do? We have 2n squared plus 7n plus 6, all divided by 6. If you remembered your let's practice factoring. So there's, as I said before, there's multiple ways to work this, and we could meet in the middle, like I mentioned before. But I want to try to show an example of how do you factor something like 2n squared plus 7n plus 6. We want we want a times c. When we distribute, a times c has to equal 2. B times D needs to those need to multiply and equal 6. So I'm thinking of foiling. Where does the 6 come from? I just pop on if you showed that early. What's up, Arlene Stanton? 6 dividing by 6 comes from the fact that this is what we want to prove. That the sum of squares is 1/6 times n plus 1, 2n plus 1. It's a little bit of a trickier one. I like to think of this one, honestly, as this, which is the same. It's equivalent. It's just that I'm factoring out that triangle number as a term, and then an odd number divided by 3. But in any case, we want to show that it is this. The base case is true. Then we are completing the inductive step for the claim. So we assume that the claim is true for n, and now we want to show that it's also true for n plus 1 as well. So because we assume that the sum of n squares is this, now we want to see what happens if we add n plus 1 squared to it. Do we end up getting the same format of, or does the claim end up being true for n plus 1, which would be this? If n is n plus 1, this last term is going to be 2n plus 3. We want to show that the right-hand side ends up being this polynomial. Okay, so factoring 2n squared plus 7n plus 6. We want BD to equal 6, AC to equal 2, and we want AD plus BC to equal 7. Okay, so AC equal 2. What are the factors of 2? Really, 2 is prime, so our only options are 2 and 1. So I could just assume that A is 2 and C is 1. I think that's a pretty reasonable guess. So 2 and 1. Now, that simplifies our factoring. A is 2 and C is 1. So then we want to find B and D that multiply to 6, and 2D plus B equals 7. So factors of 6. 6 is 1 times 6, and it's also 2 times 3. And those are our only options in integers, in positive integers. So from either of those pairings, double plus the other, in either of these cases, double plus the other, do either of these work? Yes. 2 times 2 plus 3 is 4 plus 3 is 7. So then taking D to be 2 and B to be 3 works. Over time, you get used to doing these in your head and seeing them more directly. We want 2 times this number plus these two multiplied together to add to 7. So they work, this factors this way. I wanted to show a process of factoring a polynomial because I know we haven't really treated factoring polynomials as a topic yet in the video series. So I'm assuming that you all are reviewing a lot of these topics, and sometimes I'll say, like, oh, remember from factoring and go reread enough of that section to learn this topic. And I think that that's good teaching. I think that that's good pedagogy for the purposes of this series. Because we don't need to go fully in depth and work 50 factoring problems before we learn something more interesting. Like, I think that this is more interesting. It's new math. It's useful. It's interesting. it's less dry than just learning factoring in and of, like, just for the sake of factoring. It's cool to see factoring being used somewhere. So here's a place where it's being used. But again, as I have mentioned many times, you could have taken the left-hand side and gotten to some midpoint. You could have completely distributed. And then take the right-hand side and expand it out to the same point where this is also fully distributed out, and then see that the left-hand side equals this middle term, and then the right-hand side also equals the middle term. Therefore, the left-hand side equals the right-hand side. That's another perfectly valid proof strategy for something like this, like meet in the middle. And this would not have required knowing how to factor a polynomial. It would only require learning distributivity, which we've done already in the series. This is like our second strategy that would have worked here as well. Anyways, at this point, now this is the right-hand side with n equals n plus 1. Thus, the inductive step is done, and we're complete. Like, we've shown the base case and the inductive step, and then therefore the claim is true for every number. I could write that out, but yeah. Any feedback, y'all? Like, do you feel like learning induction right now is valuable? or does anybody feel like it was a detour that was not valuable? Because I think that we can show some really cool, interesting math facts. Like I can pull in some new interesting things. I feel it was invaluable. Awesome. Yeah, that's great. I'm glad that you feel it was invaluable, for real, because we can prove so many things in math using induction. Like, it's one of the most useful tools that we have in proofs. So Lang 16.1.9 does exactly binomial coefficients, which I mentioned earlier. Binomial coefficients. This is a cool exercise that he has. Let nk be n factorial divided by k factorial times n minus k factorial. So just trust me, just believe that this is useful right now. Like, we're going to define a binomial coefficient to be n, choose k, and I can give a lot of motivation and color around this that motivates how this is related to counting. But for the sake of this exercise, he just says this, where n and k are integers, and are integers greater than or equal to 0. So I use the symbol n to say that n and k are greater than or equal to 0. 0 needs to be... k needs to be between 0 and n. And 0 factorial is defined to be 1. This is a harder problem. Prove that part A. N choose k is equal to n choose n minus k. Secondly, n choose k minus 1 plus n choose k is equal to n plus 1 choose k. So if you show these two steps first, then you can show prove by induction that for all numbers x and y, we get this. So we can prove by induction this higher degree binomial theorem. In the book, we've done this for the square term, the cube, and the fourth degree. And I mentioned this briefly earlier in this video too. So we don't have to work this one. It's a little harder, I think, but it is a classic example of a proof by induction as well, and how this technique is just super, super useful. Oops. This last one is plus 4ab cubed plus b to the fourth. Cool. So my point of writing this out is that this is an excellent first exercise as well, if you want something a little tougher. And it connects to these formulas that we've done in section 1.3. In section 1.3, we're doing these, and if we add induction, we can prove that this pattern always works, that the coefficients match Pascal's triangle, which is just such a delightfully cool fact. So this is a quick way to find binomial coefficients. For those who haven't seen this, what I'm doing is I'm adding two elements of the previous row to get the next element between them in the next row. And we kind of treat this like adding 0 and 1 to always get 1s on the ends of every row. And then adding 1 plus 6 is 7, 6 plus 15 is 21, 15 plus 20 is 35, 20 plus 15 is 35, 15 plus 6, 6 plus 1. So following, these are going to be the coefficients for the higher terms of this binomial theorem. And most importantly, it's just that induction is super useful. We use induction for so many things in math. How are we on time? We're just a little bit over. Does anybody have any questions or feedback, thoughts, requests? Anybody have any like suggestions for the stream, for the channel? Please note, y'all, that I do have a separate channel now that I've created to separate the practice streams. JC practices maths right now is I separated all the practice streams, which are usually not focused on this book. Nope, this was really good. Thank you. Awesome, dude. Thank you. I'm glad you liked it. youtube.com/@jcpracticesmaths. New channel dedicated to the Study With Me streams. So follow that if you haven't seen it already. Since you all are here, I would love to quickly tell you, I'm honestly particularly proud of episode 8. And if you're watching right now, you can watch the whole thing, but the beginning is very accessible to anybody. This sequence is so much freaking fun. Like, no joke, this sequence is amazing. I actually love this sequence of numbers. And it's a puzzle, and I'll let you think about whether you want to, like, I could just explain it right now with you all, or let you try to figure out the puzzle on your own. I think that this is something I want to be showing to all the little kids that I'm tutoring. This is my favorite new method to practice addition. So if anybody doesn't want to see the solution to this, please drop off the live stream right now, because this will be the last thing I do today. But if anybody does want to just see how this works, I'll explain it right now. But you can also see this in more depth. I'd really appreciate it if you all watch that episode and leave a comment if you enjoy it, because I think this one's actually super cool. Excuse me. Okay, so here's a chance if people want to see this. I'll explain this one again right now. Let's do one last one. The next two numbers are these. You'll go watch the episode. Thanks again. Yeah, awesome. Watch the episode. I'll give the rapid fire version here, but the episode is more polished. Really nice to have you here, Fred. Thanks for being here. Thanks for watching. Okay, so for those who want to watch it now and maybe ask questions or anything like that, this is such a damn cool sequence. The way I'm doing it is I'm adding odd numbers descending. So what is 24 plus 9? 33. Plus 7? Plus 5? Plus 3? Plus 1. And then once I've finished adding down to... Once I've gotten to plus 1, then I reset and I start with the next odd number. So you'll see that we are starting with odd numbers and we're creating groups. So that's, each of these red lines are one group, and they all start with the next odd number. And then we add odd numbers descending. I call this reverse odd sums. So 15 plus 13 plus 11 plus 9 plus 7 plus 5 plus 3 plus 1. 17 plus 15 plus 13 plus 11 plus 9 plus 7 plus 5 plus 3 plus 1, etc., etc. And we continue. One of the coolest things about this is that it's a tough addition challenge, to try to keep track of these things in your head and add numbers, just thinking that plus 5, that plus 3, that plus 7, that plus 13, rather than thinking 24 plus 13 is dot dot. Like, it's good at, I think, trying to reduce sub-vocalization somewhat. Like, plus 5, plus 3, plus 1, and trying to make it like more automatic, like adding numbers. So addition may not seem valuable to practice, but it really is. Like, it's such a fundamental skill that if you don't have quick addition fluency, then it's going to slow you down in other things. But then also just for teaching kids and stuff, and finding a beautiful math pattern. Like, if you add odd numbers, they always add to square numbers. So what I was going to say is that not only is it great to practice mental math and practice addition, you can check your own work and you can know if you made a mistake somewhere along the way. Because 81 is 9 times 9, 64 is 8 times 8, 7 squared, 6 squared, 5 squared. So it's super cool at just like catching your own errors while you do like mental math practice and getting faster at addition. And then guess what? We can prove this by induction. Back to induction being such a valuable tool. This pattern will always work. Like, I'm very confident. I'm extremely confident. I know for a fact that this pattern will always continue working. It's not just a coincidence that works for the first 100 rows or something of this sequence. Which is really pretty amazing. Pretty amazing to be able to know these mathematical truths that are true for all numbers. So back to the idea of like induction being really beautiful. It really is, because it's so useful in so many different places in math. All right. Thank you for watching. So live streams are here now. If anybody wants to consider joining the Zoom group, it's really fun, dude. Like, this is great. This is certainly great. But the Zoom group is even better. If, like, I'm not gonna lie, it's even better. So Zoom, you can join first one free. Send me an email, jcpractices@gmail.com. I'll send you the link. And we meet on Saturdays at the moment at 11 a.m. ET, which is plus 4 is 13 o'clock GMT. All right. Thanks everybody for watching. It was a pleasure to practice math with you all. Cool. Thanks for watching. I'm gonna go. Bye. Bye everyone.